So this chapter is a very brief and simple overview of computational aspects in the context of modeling of heat and mass transfer processes. It is intended for an undergraduate course in engineering. We will cover the finite difference and the finite element method eventually. So here is how this chapter fits in the overall schema of a modeling course. So chapters 1 through 5 covered a number of things, starting from problem formulation, where you take a problem in the physical world and develop the mathematical analog. That's, you replace the physical problem into a mathematical one in terms of a governing equation and boundary condition. Then you solve, and then you do things like validate the model and you perform sensitivity analysis. So when we did these steps, all of these, we kind of put aside the theory because, well, it's a one semester course and we have to get through developing a model. But the theory we need to eventually have some idea about. And so now we are in this part. And we talked about the governing equations and boundary conditions. Then we talked about source terms for like heat transfer. The source terms come from different physics like microwave heating or laser heating. For mass transfer, the source term can come from kinetics of a reaction. And then finally, we get to the numerical methods. The numerical methods are the details of the solution process. So the solution process really has quite a bit of theory in it, and that's really what we're going to talk about at the end. But again, we will do a very, very gentle version of it. So eventually we will talk about the finite difference method and the finite element method. So why do we care to know more about the solution process? Because a black box approach, it simply does not work. A black box approach to the solution process simply does not work. A real possibility is this GIGO that you may have heard. It stands for garbage in and garbage out. Okay, this is a real possibility in numerical solutions. Trust me. So proper use of the software requires knowledge of the solution process. So you really need to know about the solution process to be able to use it properly. And the other part is complex problems require tweaking of solution parameters. So you really have to know enough of the solution process to make it to work. And that's the reason we really have to learn at least a minimum amount of the solutions process. So before we get into the details of some of the solution techniques, just to recap a little bit of differential equation terminology. For example, ODE is ordinary differential equation, whereas PDE is partial differential equation. Now, what is an example of ODE? So an ODE in our context could be this equation of a kinetics. Okay, so this is an ODE because C is a function of time only, one variable. On the other hand, if I have the full diffusion equation without convection, so it will look something like this: d del square c del x square plus or minus kc. Okay, and so in this case c is a function of x and t, so two variables. That's why we write del instead of d, if you recall, and it's a function of two variables, x and t. So what is the order of a PDE? So in this equation, for example, the order is 2 because that's the highest order derivative. What is homogeneous versus inhomogeneous PDE? So this equation, for example, is inhomogeneous, and if I write the homogeneous version, then you'll know what's the difference. So this is homogeneous. So by having a term like this added, so which is basically the source the source term added to this is going to make it non-homogeneous, and it brings additional complications. So linear versus non-linear, as it says, dependent variable or its derivative are order 0 or 1. We are going to be dealing with some non-linear terms. So when can things get non-linear? So suppose diffusivity is a function of concentration. Well, then this same equation would be written as del C del T del X of d del C del X, because d is no longer a constant, and then it becomes nonlinear. Contents of this chapter is going to be first to talk a little bit about limitations of analytical solutions and the flexibility of numerical solutions, then talk about two different methods of numerical solution that are very common, and then these two methods lead to algebraic equations. These two methods lead to algebraic equations. So how do we solve linear algebraic equations? And then finally estimating discretization error in finite element method and its reduction. So those are the contents. So first, we want to have a general idea of the benefits of a numerical solution over analytical. So here we want to just contrast numerical solution with the analytical solution process. So in analytical solution, you have a differential equation. You start from a differential equation, which is the governing equation, the boundary conditions for a process, and you kind of solve it. And the solution process, this can be done by hand calculations, or it can be programmed in some software, but these are pretty much the exact solutions to this differential equation. Whereas numerical solution, the differential equation, again this governing equation, boundary conditions for a process, is converted to a set of algebraic equations. They are really approximate, they're not exact, and so these are approximate, these are not exact, and then those equations are solved. And how you convert these differential equations to algebraic equations, differential to algebraic, it can be by many different methods, many different numerical methods. The one that we will spend time on from this list is the finite element method. So here we discuss the limitations of an analytical solution using a simple everyday example of heat transfer. So let's look at heat transfer in this slab, and it's a 1D heat equation that's being cooled in this case symmetrically. So this is my initial temperature, this is my boundary temperature on both sides, so it's a cooling process and it's symmetric. So my governing equation in this case for heat conduction is alpha del square T del x square, where alpha is the thermal diffusivity and the boundary condition is T at x equal to L is equal to Ts, and del T del x at x equal to 0 is equal to 0. That's the symmetry condition. And then initial condition is T at all x at t equal to 0 is equal to Ti, a constant value, this one. Okay, so these conditions lead to the analytical solution this way that you have done in math class and in heat transfer class. So we are very much used to writing these conditions like this one, T at x, or this one, or this one. So we're very much used to writing this in a math context, but when you translate this into reality, these are serious restrictions. These are serious restrictions that are hard to satisfy in a real process. So for example, let's start with the geometry. So all this process, this solution, by the way, the solution is plotted here. So these are the profiles that are plotted out of this solution. This is T as a function of position at different times. Okay. So these solutions assume that it's a uniform slab geometry. You cannot have a hole in there. That's not allowed. Or you cannot have thickness, this 2L, the thickness, it cannot change. Okay. What's another restriction? The boundary temperature. So it's nice to write this one, but this means this boundary temperature cannot change with time. If it changes with time, this is not the solution. In fact, in general, we cannot solve such a problem. Then what's another restriction? Uniform initial temperature. Okay, so initial temperature in this one is a constant, but let's say think of our body. So if we start from any condition, it is in equilibrium, inside is warmer than the surface. So the initial condition isn't going to be a constant. And if the initial condition is not constant, like it's written here, then this solution will not work. This solution will not work. This one will not work if the initial condition is not a constant. So these, another one is, you notice that this alpha is sitting outside. So it's treated as constant. It's a constant. And only under that condition you can come up with this solution. If it is not a constant, you cannot do this. So what does that mean? What is alpha? Alpha is K over rho Cp. Now, when you heat and cool something, the thermal conductivity as well as other properties, they change with temperature. And so that's very real. But if you say alpha is changing, then this solution is no longer valid because this is for a constant alpha. So what this means is for practical situations, we need solution methods that are more flexible than this one. This one is not as flexible because it has all of these and many more restrictions. So now let's see if we can convince ourselves of the flexibility of a numerical solution over analytical solution. So this little differential equation here actually does not have an analytical solution, but we will still solve it. We can solve this one and not going through analytical solution, but a completely different procedure. That's what is numerical solution. So we can approximate the derivative df dx as f at x plus delta x minus f at x over delta x, and that's equal to e raised to x squared. So if we simplify that, we can write f at x plus delta x is equal to f at x plus e raised to x squared times delta x. So this is my algebraic equation. So this one got replaced. It is approximate. It is approximate because this guy is really an approximation, excuse me, but we're going to treat it as equal, which means we are making some errors in here. And so if we try to use this new solution, so if we will use this one to plot the function f versus x, so we need an initial condition where we can start from. So at x equal to 0, f at 0 is 1. So that's given. So this is my initial condition, or this is the starting point. And so that's given. Okay. So at another point 1, I can calculate it this way. So f at 0 plus a step size delta x equal to 1. So this is my delta x. Okay, delta x is equal to 1 is equal to f at 0 plus e raised to 0 square times delta x is 1. So f of 0 is 1 plus e raised to 0 is also 1. So that is equal to 2. So that's what is plotted here. And the next point would be f at 1 plus 1. Okay, so now this time x is 1 and delta x is again 1. So we look at the next point. F at 1 plus 1 is equal to f at 1 plus e raised to 1 square times 1 is equal to f at 1 is 2. So it's 2 plus e. Okay, so we see the value for the next point. 2 is this one. This is my 2 plus e. This is supposed to be 2 plus e, and this one is supposed to be 2. Excuse. And so we can keep going. We can keep going for the next point and so on, and then we can join it by a line, and we actually have the solution that we're looking for, f as a function of x. So the big deal is we could solve for f as a function of x, and we didn't need to know the analytical solution. We could still do it. Now there are some special things about this. One of them is that this procedure that we went through, okay, writing in terms of replacing the derivative in terms of a finite difference, this numerical method can work for arbitrary equation. It's not just related to this equation. Any place I can replace the derivative. But this type of solution has some special things. That is, you notice that you only solved here and here. You didn't solve anywhere in between, and you can join it by a line. So you could say, well, that's not as good. It's not as smooth. Well, we can improve this solution. All we have to do, we can improve the accuracy by just reducing the size. Now, let's not call it the element size. Let's just say by reducing delta x. By reducing delta x, we can improve the accuracy. So we can get closer and closer to a smooth solution. But that would be at the cost of more computation. So more computation is going to require more memory, more time, but those things have become cheaper and cheaper over time, and that's why these kinds of numerical methods have really taken off way back in the 1970s.